All right, good morning, good people. This is me again. I am here with another video, um, continuing section C of the syllabus, waves and optics. Today we will look at light. Okay, today we will look at light. Now, light is an electromagnetic wave, first of all. I should use EM, an EM wave. It travels at a brisk 3 by 10 to the 8 meters per second, give or take a few shakes. Now, um, the reflection of light. Like I said previously, all waves are expected to reflect, refract, diffract, and interfere. We will now look at reflection. So let us go. Reflection, Reflection. Well, the reflection of light is pretty straightforward. If we have an incoming or incident ray of light and it makes contact with a surface and then it bounces off, reflection has occurred. Now, there are two laws that govern reflection. So if we, for the sake of argument, construct a perpendicular, yes, a perpendicular to the surface, the ray of light hit, we use this perpendicular, which is called the normal, yes, the normal, to create two angles, this angle and this angle. This is called the angle of incidence. I is the angle of incidence, and this R is called the angle of reflection. This is the reflected ray, REFL, and this is the incident ray, INCI, incident ray. Now, the two laws, yes, two laws of reflection are as follows. One, I should not put that till there. The first law, I hat is equal to R hat. Simply put, the angle of incidence is equal to the angle of reflection. And the second law states the normal incident and reflected, REFLECTED, rays all lie on the same plane. On the same plane, PLANE. This is the first law. Well, this is the second law of reflection. And that's it. That's reflection for you. Nothing complicated. The next thing we move on to is refraction. Now, refraction of light. By definition, refraction is the bending of a wave. This is the bending of light as it passes from one medium to another. Best example is air and water. If this is air and this is water, we can construct a pair of normals, perpendiculars. The reason I'm using a pair will be seen shortly. And we can have a ray of light, one ray, traveling from in the water to the air. And we could have another ray of light doing the opposite, traveling from air to water. Now, do note that this is your angle of incidence, and this is your angle of refraction. Refraction. This is your angle of incidence, and this is your angle of refraction. Not reflection, refraction. So, there are two laws, just like reflection, that govern refraction. The first law states, well, the first law is what we call Snell's law, S-N-E-L-L''S, Snell's law. Snell said that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant, which we call the refractive index. Alright, that's what it's called. Should probably use a darker color. Refractive index. Now, this refractive index is equal to two other ratios. The first ratio is the velocity of light in the first medium to the velocity of light in the second. And this is equal to something else as well. The wavelength in medium 1 to the wavelength in medium 2. Now, the question is, or should be asked, which medium is medium 1 and which medium is medium 2? Well, medium 1 is the medium you're leaving. Medium 2 is the medium you're entering. You're leaving this, you're entering that. That is how it works. Now, in some cases, the refractive index is even stated to indicate this. If you see 1 and, well, I call it N, 1 and 2, it means you're going from 1 to 2. If you see 2, it means you're going from 2 to 1. Well, whichever medium is medium 2. You could name them, because in some cases you will actually see air, water, and in some cases you might just see a number. But it's always good to make note of which medium you're leaving and which medium you are entering. Quick explanation. Refraction occurs as a result of a change in velocity. Velocity changes. The change in velocity occurs because of a change in wavelength. If you remember, in the formula for wave parameters, V is equal to F lambda. The frequency cannot change. Frequency is what gives light that, well, frequency is my words are so muddled at the moment, but each color we see has a specific frequency. When light bends, it's not that the colors change. Alright, the colors or the frequency remains the same. What changes is the wavelength. Alright, just putting that out there. Now, the second law of refraction is kind of like the second law of reflection. It says the normal, incident, INCIDENT, and refracted, this is the only difference, refracted rays RAYS all lie on the same plane, PLANE, and this is refraction. Now, refraction continues into something called total internal reflection. Total internal diffraction. And this is a process. Well, actually, it is the byproduct of a process. So let us assume we have a block of glass, right? We have a piece of glass, and we are shining light from within the glass the light will bend like this. Right? When you're moving from a dense medium to a less dense medium, you tend to bend away from the normal. That's air. This is glass. This is your angle of refraction. This is your angle of incidence. Now, if we keep increasing, if we start to increase this angle of incidence, we will also observe an increase in the angle of refraction. Right? It's not necessarily going to be a one-to-one increase. Right? So increase I hat, and yes, you increase the angle of incidence, which causes CAUSES an increase in R hat. Now, from this stage and phase, you end up at a point, if you keep increasing the angle of incidence, right, you end up at a point where our goodly little ray of light no longer leaves the glass. Oh no. What our angle of, and please note, these are sketches, right? This is not like a representation of where the angle would be, right? It's just a sketch. The ray of light travels along the boundary between glass and air. Now, this is your angle of refraction, and this is your angle of incidence. At this point, I should probably use a different color. Let me use blue. At this point, angle of refraction is 90 degrees. Now this is very important because the value VALUE of, I should just put I hat, the angle of incidence is called the critical CRITICAL, the critical angle. I nearly put the critical angel. Yep, I almost did that. The critical angle. It is said that total internal reflection begins at this point. Alright? Let me make a note of that. TIR begins. Now, if we are wicked and we still increase the angle of incidence even further, we end up, as my grandmother used to say, we reach where we go in. That line is far from straight. I did not put my little, yeah, good, those things. Now, what happens is, and again, this is not drawn to scale, this is just a sketch to illustrate what happens. The ray of light is now reflected internally. Don't forget, let me explain what internally means, right? Don't forget, this is air and this is glass. This ray of light is, you could say it bounces, BOUNCES, bounces back into the glass. And if you just rewind this video ever so slightly, you will see that this looks just like reflection. we have an angle of incidence, and we now have an angle of reflection. And I could say TIR is completed. COMPLET is complete. Yeah. Now, there is a formula you must remember. Yes, formulae are vital. Sine of the critical angle is equal to 1 upon the refractive index. Right? Sine of the critical angle, refractive index. Please make sure you calculate it in degrees and not radians when you're doing these calculations. Thank you. And this is TIR. Now, quick note. An application of total internal reflection is fiber optic cables. I mean, most of us should be getting internet these days via fiber optic cable, and the fiber optic cable makes use of total internal reflection to basically pass a ray of light down a very, 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 very tiny tube. That's basically it. Now, we move on to the last two, diffraction and interference. Now, diffraction, D-I-F-F-I, that does not look like an F. If you have the time, get a sheet of cardboard, punch a small hole in it. Alright, this is a sheet of cardboard. Punch a small hole in a sheet of cardboard, and then get a light source and put it on the other side of light source. Put it on the other side of the sheet of cardboard. If you now bring this sheet of cardboard close enough to a wall, what you will notice is that there is a spot of light on the wall that is much bigger than the hole. That is because light coming out of the tiny hole you made spreads, that should have been orange, sorry, spreads as it travels towards the wall. So it might start off very, very, very narrow, but it could end up being very, very, very wide. It's like a torchlight. A torchlight has a very small aperture or opening, just a circle. But if you look at the beam of light coming out from a torchlight, it is very wide. And that is due to basically diffraction. Now, diffraction, and I did not mention this with sound, but I should be ashamed for not mentioning with sound. Diffraction has a condition. The condition for diffraction is gap width, WIDTH, or opening, NING, opening, should SHOULD, should be smaller than the wavelength of the wave. This is the condition for diffraction. Now, if I remember correctly, green has the wavelength of 550 nanometers. Let me write that down. 550 by 10 to the minus 9 meters. Alright? Take a meter, divide it into 1,000 parts, and then divide it into 1,000 parts. Well, divide it into 1,000 million. That's the best way to put it. Divide it into 1,000 million parts, and you're going to find out how small, I was about to say wide, how small the wavelength of light is. Now, for diffraction to be done with light, it either has to be accidental or really, really intentional. Like, you have to be very precise. And we will look at this in the next video. As always, if you have questions, please feel free to ask me directly. Those of you who have my contact info. If not, you could always leave the questions down in the comments. Anyways, as always, stay sane, stay safe, and I'll catch you in the next one. Bye bye.